David Margolin invited me to provide a forecast discussion for the subseasonal forecast contest. And so as my first discussion, I wanted to provide an overview of the different large-scale conditions of the tropics and how they may be impacting the large-scale atmospheric circulation. In the future, I may add different aspects to the discussion. This is my first time using the QuickTime recording system, and so a bit of this is experimental. We're going to start by looking at the present patterns in sea surface temperature and how they've been evolving over time. The large-scale total sea surface temperature pattern reflects the normal northern summer pattern with a little bit of anomalous central Pacific warmth associated with an El Nino condition, while the cold tongue in the East Pacific is starting to come back up. The warmest waters in the world presently are along the equator of the central and eastern Indian Ocean, extending in a region through the northern parts of the maritime continent across the Philippines and over the northwest tropical Pacific Ocean. This maximum temperature near the dateline is anomalous and is a sign of the present El Nino condition. We then examine the present condition in anomalous sea surface temperature. We can see positive sea surface temperature anomalies in the central and eastern Indian Ocean. Years when the monsoon in India is weak tend to be years with higher sea surface temperature, in part because the wind response to the monsoon drives a wind evaporation feedback, which reduces ocean temperature. But the Indian Ocean also has a substantial fluctuation in sea surface temperature in response to subseasonal phenomena like the MJO. The southern maritime continent region is anomalously cool, but like that sea surface temperature maximum in the total sea surface temperature, we have an anomalous warm signal that extends northeastward from the Indian Ocean across the maritime continent, the Philippines, to the northwest subtropical Pacific region. There is a relatively weak region of anomalous warmth near the dateline, though this implies quite high absolute surface temperatures. While the East Pacific has a mixed temperature anomaly pattern, with cool extending off the west coast of South America and some places right along the equator, you see these fluctuations right here. They're associated with what's known as tropical instability waves. These are westward moving waves that amplify on the north equatorial front, on the northern side of the cold tongue. And these warm anomalies you see alternating with the cold anomalies here are associated with meridional circulation signals associated with these waves. Sometimes these waves align with the buoys in the tau array, and that leads to aliasing and unclear signals in the tau database. Imagine, for example, what would happen if the warm anomalies lined up with the buoys over the East Pacific, while the cold anomalies were in between them. The tau array would then make the signal in that region look warmer than it actually was if you had averaged over the whole region, knowing what was in between. This cool region of the East Pacific has emerged relatively recently and is associated with subseasonal variability, but it might also indicate some gradual shift in the low frequency structure associated with the El Nino pattern that's presently in place. It's easy to express too much confidence in what direction the El Nino signals will be going in the next few months. Many people might see the emergence of these cold anomalies as the end of the El Nino event. And that's a possibility, but it could also develop like this just due to subseasonal fluctuations, and the warm signal emerge again over the next few weeks. The TAU data are not available at every point along the equator where they would normally be found, because some of the buoys haven't been maintained in light of either pirate attacks or just wear and tear on the system. So I'm looking here at the TAU buoy data at 2 degrees south to try to get a feel for how the subsurface ocean conditions are evolving. This is the 5-day period ending on July 4th, and here's the corresponding 5-day period ending July 9th. Let's toggle back and forth between them a little bit and kind of get an idea of how things are trending. It's a little bit of cool anomaly right at the surface of the East Pacific, but the general trend is toward eastward movement and expansion of the warm anomalies subsurface. These warm anomalies are being driven by a westerly wind event associated with the MJO that I'll show you in a few minutes. In the weeks leading up to this westerly wind event, there was a substantial trade wind surge. It wasn't particularly anomalous, but it's different from what we've been observing in recent months. And so, as you might think about it, the ocean comes into some kind of quasi-equilibrium in its geopotential surface with the east to west wind stress that's normally felt in this region. And if that wind stress has been weaker than normal, as it has been recently, then the ocean geopotential surface is also a bit weaker than it would normally be. And so then a surge in the trade winds is going to act to build the geopotential in the western basin and lower it in the eastern basin and produce an upwelling effect along the equator, which induces cooling. But then that easterly trade wind surge is typically followed by an MJO westerly wind event, which we're observing right now. So the net effect of the competing easterly and westerly subseasonal forcing on the ocean over time must allow integration of the full forcing over time. And what direction it goes in the long run depends on how the next MJO events evolve in connection with the subsurface anomalies. We're looking here at upper ocean heat content anomalies in degrees Celsius, showing the, let's bring that back here. This is what we're trying to show. The El Nino signal is associated with this anomalous warmth over the eastern basin and amplifying anomalous cold in the western basin. And the strongest eastward moving event right here is a downwelling oceanic Kelvin wave that grew in response to a westerly wind event that occurred back here associated with an MJO. But these downwelling warm events have been reducing in amplitude over time, suggestive of a possible trend toward a weakening of the El Nino event. But we also need to realize that many past El Nino events that didn't have particularly strong warm anomalies along the equator during the summer tend on average to be associated with weaker MJO westerly wind events on the equator. And they also sometimes reverse and go toward a neutral or ENSO cold condition, but other times they re-amplify in the late summer or fall. 1986 was an example of such adjustment where a fall amplification produced fairly strong El Nino conditions that year when the preceding northern summer conditions weren't all that impressive. Now we're looking here at the upper tropospheric wind anomaly in the CFS reanalysis, beginning back in March and going forward in time. Time is going up. These diagrams are courtesy of my former graduate student, Kyle McCritchie, who earned his PhD and is now employed at the Climate Prediction Center. You'll notice a general tendency of westerlies to outdo easterlies over the western hemisphere region, while conditions near the dateline have more upper tropospheric easterlies. And these are generally consistent with a weak El Nino condition. As the CFS model goes forward, it typically produces more westerlies over the western hemisphere than actually occur. But these are associated with development of El Nino conditions, in this case, in the model concentrated near the dateline. Now, superimposed on this general signal of increasing these westerlies is fluctuation between easterlies and westerlies in these west to east moving regions. These are the MJO events as they express in the upper tropospheric zonal wind. So crossing the western hemisphere, the Pacific phases of the MJO are typically associated with westerly wind enhancement crossing the western hemisphere. And then preceding new Indian Ocean events, these easterly wind signals cross the western hemisphere and then yield mass divergence over the Indian Ocean when they arrive there. That helps to excite convection in that region. Now, the model doesn't simulate the MJO signal particularly well over the western hemisphere in the circulation or in its arrival over the Indian Ocean. This model, the CFS, tends to overdo amplification of MJO signals over the Indian Ocean, and it also tends to propagate them eastward too slowly. The effect may associate with convection over here, but it may also be driven by the signals that are actually driving the movement of the circulation signal around the world. The development of these easterly wind signals here in the CFS and in the real world we're looking here at CFS weeks 1 and 2, 200 hectopascal vector wind. We've got week 1 at the top and week 2 at the bottom. And we know in that longitude time diagram that the upper tropospheric wind shows amplification of western hemisphere easterly wind along the equator. This time of year, that amplification is typically associated with a wave train moving across the southern hemisphere, breaking ridges onto the equator, which through geostrophic adjustment accelerate easterly wind here. And then on the back side of the region of accelerated easterlies, upward motion produces deep atmospheric cooling, which then changes the easterlies which were originally in a trough to easterlies, in a ridge, to easterlies that are in a trough, which then becomes consistent with a Kelvin wave, which then propagates the signal eastward, arrives over the Indian Ocean, and helps to enhance the development of the next MJO convective phase. But given that the CFS has a bias toward too strong and too slow convection over the Indian Ocean, and that the model shows a fairly weak and slowly evolving signal over the Indian Ocean over the next several weeks, I would argue that this signal is likely overdone. There is a real Indian Ocean event coming up, driven by circulation signals coming around the world. but that signal is likely to be too strong in the model and too slow. Nevertheless, it will have some effects around the world, which we can anticipate associated with MJO superstructures. You consider the circulation response to MJO convection includes Rossby waves that propagate across the middle latitudes, even over the poles, and change the weather around the world. Now we're focused on northern hemisphere summer conditions right now, and it's typical that MJO signals are a little weaker during the northern summer than during the northern winter, and the Rossby wave response to MJO convection over the northern hemisphere is also substantially weaker, as most of the energy forced by the MJO goes into the winter hemisphere. Nevertheless, a nonlinear wave pattern of blocking ridges and subsequent downstream development, trough anomalies followed by regions of intense mid-latitude precipitation on the equatorward and eastern side of those troughs induce ridge signals downstream, and the signal perpetuates itself even though linear Rossby wave propagation is quite unusual in the summertime. So we have typical effects this time of the year, moving toward the middle and end of July, of MJO signals in the Western Hemisphere. We're talking phase 1, signal arriving over Africa and the Western Indian Ocean. This is a statistical model of the average seasonal evolution of MJO events at all times of the year. You can copy and use this website as you wish. Swiping from left to right is changing around the seasonal cycle from January back to December. And going down on the diagram is shifting the real-time multivariate MJO index phase from 1 through 8. So we're beginning in phase 1 here. We expect a region of enhanced convection near Central America, a little bit over the Atlantic and West Africa, and also developing over the Eastern Indian Ocean with a region of suppressed convection extending from northwest to southeast over this area over here. And there's a tendency during the northern summer for the warm phases of the MJO for the Midwest East United States region to be the Indian Ocean and Western Hemisphere phases. And we see as the condition moves forward across phase, there's a tendency for a block to form over Western Canada, and then subsequent development of a trough anomaly. We may be seeing these signals beginning to emerge at the end of July into early August. So this is what you would expect to see in the average MJO event this time of year, evolving from phase 1 across through phase 8. Now, actual outcomes will depend on the associated distribution of convection, how mid-latitude weather systems along the wave train response behave, tropical cyclone response patterns that can feed back on and alter the progression of the MJO and its circulation response, as well as signals in low frequency variability, which we haven't yet discussed other than looking at the ocean condition and suggesting that we have right now a fairly robust, not particularly strong, but nevertheless robust Central Pacific warm signal. So I'm going to show one more thing. I'm going to have to switch between windows here in order to pull up the one I'm most interested in. I want to give some illustration of what the present low frequency favored signal is. This is based just on the organization of low frequency tropical convection, which has a little bit of enhanced activity near the dateline right now, somewhat suppressed convective activity over the northwestern Pacific and some other regions. This is the 200 hectopascal geopotential height signal at present that we expect on average is associated with this seasonally evolving ENSO forcing structure. As we go forward in time, there's a tendency for late July and August to have warm state patterns. Now, through most of the second half of July, these things are in phase with the Indian Ocean MJO forcing, which suggests substantial warmth in the eastern United States, troughing somewhere in the interior west, which is going to favor rainfall in the Midwest region right here. But going forward through August, this is how the seasonal evolution, given the present state of low-frequency tropical convection, would favor conditions changing. So coming later into August, blocking becomes a little bit more favored over the North Atlantic, and the ridge in the northeastern U.S. starts to backtrack into the central United States. Now again, this ignores all subseasonal and synoptic variability. This is what the low-frequency pattern, if it maintained its present structure with some seasonal evolution, would project moving forward in time. It doesn't account for how the ocean conditions may be changing over time. And that's the end of the low frequency portion. I would appreciate feedback on what I've included in here, and in the future I may alter the content given that feedback. Thank you.